So yeah, uh, welcome everyone to the second talk of the TED K-theory seminar. The first talk we had, like the first time we had Tim, who kind of gave an introduction and motivations for the program for the reading seminar. And this time here I am. So again, apologies because of the fact that last talk was cancelled and we had to shift it by a week. And for those of you who've been there since the beginning, and so okay, so this time I plan to talk about K-theory, so topological K-theory. So what is K-theory, anyways? Again, before I begin, I'll say this that as I mentioned, it's gonna be a really basic talk, so maybe I should apologize in advance to my a lot of people in my audience are already super familiar with all this stuff. So right. So here's the plan. So yeah, some historical chit chat means I just want to say why you call it K theory. So I'm going to start by defining vector bundles, right? Then the K functor construction. There will be a few examples, and the only thing that I thought that I would do, like, it doesn't seem to be it. So yeah, sorry about it. So yeah. Well, the product theorem, and so yeah, after examples, we'll talk about the product theorem with about periodicity, and maybe towards the end, depending on time. So you can see, I have an I'll try to, yeah, I'll try to finish before time so that we can have some time for discussion, but we'll see how it goes, right? So if possible, I'll also like talk about Waldhausen K-theory. And also apologies in advance again because like I kind of have a sore throat, so feel free to interrupt if you don't understand something that I'm saying. So right, so K theory was invented by Grothendieck. So why is it called K? I mean, it'll just be one sentence. I don't want to get into the K stuff. A lot of history. So K stands for Klassen, class. So the story goes that so instead of because of the fact that C of X means like continuous match, from X to wherever, like instead of continuous match, right? So that is the reason. So like because of that, so they decided to call it K of X. Like, I'm not going to get into what exactly like he was doing and all that. Like we'll maybe get to that towards the end. So right. So let's start with vector bundles. What vector bundles are? So fix a K is a field. So I'm fixing a field K. Here's the definition. So a K vector bundle is a K vector bundle. I should say over X is a continuous map. So V to X. So it's that sorry. Continuous map X such that fibers. So I don't know. I'll need to note it by. I don't know. So whatever. The fibers are K vector spaces. K vector spaces such that I'm kind of putting it a bit loosely. There are they're compatible. So they're compatible with the topology induced as a subspace, like induced as a subspace, right? So what does that mean? Again, I'm sorry, like for the handwriting part. Right. What does that mean? So that means that, like, this is something like this, right? I don't know. Just putting it naively. Oh, sorry. I just realized that my video's off. So, yeah, I don't think that's a problem. I can turn it on if somebody. Okay, let me. Okay, so there exists an open cover, and you have this n that is the rank at a polymorphism. Remember, case the field that we fixed. That is fiberwise K linear. Oh, sorry. Fiberwise K. Right. So yeah, that's what a vector bundle is. And now, like, why do we care about vector bundles? Like you may ask, like, why do vector bundles matter? So, so for starters, this is like, so vector bundle, the theory of vector bundles, it's all like it's just like parameterized linear algebra, right? So, and also they appear like a lot of so physics people understand, like they appear in Chern wave theory, for instance, like so vector bundles are really hard. So let's see an example of that. So an example. So yeah, let me try and look up an example. So let's set subset of R2 such that XY is 0. By the way, when I'll upload the notes, I'll make sure that like handwriting situation is sorted out. Like I'll try to write it down again. So I'm really sorry about it. XY is equals to 12. But let's look into this then, and then you look at the projection, projecting it first. So that gives you a family of X spaces, right? So that will give us so it's basically this map. So as we saw, this map, and so the conditions that the fibers gave X spaces. So had to do stuff. We'll see more examples, but further, let's define a few things. For like the bundles, so let's consider. So this is the way I'll denote a vector bundle. So for vector bundles, or like in different ways, like you look at it. So for these two vector bundles, right? Morphism. It's just it's a continuous map V to V dash. So it's the dash also. So like basically F respects this, like this map that respects these projections, like these maps that you have, whatever. And for all X F restricted to so okay, what does this mean if restricted to F6? So X, remember this lowercase x, it's like an object of the total space. x of our x that we have. Okay, so it is linear. Okay, it's not been great so far, so I think it's gonna take way longer than I expected. Okay, I guess. So in fact we have a category. We have a category. Right, we have a category of all vector bundles with the maps being vector bundle homomorphisms, right? So the big picture, like what we want to do is like we want to we want to understand. So we want to understand this like in the isomorphism classes of vector bundles, like for an arbitrary x, right? So this is hard. This is hard because the classification, so the classification that you have, this classification is in like degree -1 non-abelian cohomology with coefficients in GLM K. So hard as let me try to write it. Analyze this. So this is hard as these are classified by degree -1 with coefficients in GLM. Right. So this is right. So that is why it is hard, right? And so the big picture, like the big picture that everyone have in mind. So the big picture is that so K theory is basically K theory basically forces like this is at least the way I kind of began understanding K theory, so it kind of forces the bundles to be classified by an abelian cohomology. So K theory forces bundles to be classified by abelian homology. So yeah, we'll get more into this. Now let's move on to operations on vector bundles. So as I mentioned before, it's it's just parameterized linear algebra. So you have these very natural extensions of all these operations that you have between vector spaces to vector bundles, right? So also we'll see it really general kind of way to. Oh, by the way, I just realized something that I should have said at the beginning of the topic. The references that I've mostly used, that I've been using since the references are Atiyah's Michael Atiyah's notes and NLab. There's an NLab introduction to K theory section that's also really useful for me. Yeah, right. So just to mention right. So okay, let's see a natural way to extend these operations. So I'll call K effect. I don't know, is that no, it doesn't seem like a good notation, but okay. So there's the category of finite dimensional vector spaces over topological over topological base field. Yeah, right. So we have top. So top is my category of topological spaces, enriched functor. So this is a very general way. So we'll see how. Sorry. So we'll see how this how we get the Whitney sum, for instance. We have a topological top enriched functor. So let me call this F from K vect N. So this is just like the product category. Okay, vect. So then so this induces. So this induces a vector. So okay for an n tuple vector bounds. Right. Over the same base space, of course. So it induces another vector bound. So let me call this F tuple. Right. So that just define it fibroids as following. So that should make sense. And so we have a few examples, like for instance, okay, before the Whitney sum, let me go on. Okay, so let's suppose this function f is the determinant function. Okay, then f2 will give us. I'll just try it. Will give us the structure fiber-wise. Sorry. Fiber-wise determinant vectors. Get to that. So now if f is like your direct sum, so this is from oops. This is from, so here n would be equal to 2 k vect to k vect, right? So that so this is just a Whitney sum. So this is all so the ones in the way and cool. So see, look at my list again. Okay, so okay, now so let's talk about trivialization. So okay, so we have another example of a vector bound effect. So X is a topological space. X. And so remember, in case the field is fixed, so it is vector bound. Yeah, so that is by projection. So this is like this is called trivial vector bound rank and trivial. Right. So okay, so for a vector bound we do X, right? So if we have an isomorphism, so I say a choice of iso if exists. So it's called trivialization. Trivialization of the vector. Right. So right. So if it has a trivialization, it's trivializable, and we get a. So I'm just going to roughly say we get trivialization. It should be clear, I guess. I'm open cover it. Open cover. So similarly, so J belongs to something. So, homeomorphisms. Or and restricted to J is in so yeah. So right. So then let's we'll define what a section is. So for that, so we can we have a vector bound. We have homomorphism. Vector something like this one. Privilege, of course, which is like which. So now you think about it. Think of it as a continuous function. So because you have fiberized linearity as a whoops, yeah, as a continuous map to V, right? Such that so give it a kind of so such maps like yes, these are like the sections or also maybe cross sections, like depending on reference and effect maps, right? So okay, let's see another example. Now that we have seen what we mean by trivialization. So right, let's see maybe yeah, the tautological line. So again, so I have this is my projective space KPI, and so where K is as I said, topological field maybe. Right? So so the line bundle is so I'll write it down. Like and we have vectors. Well, right, U is basically like whoops. Just call it a like this just lambda. Span. So cool. So that gives us the so right. So that gives us our topological line model KPN. Right. So right. So I thought that I'd explain like how the get the Mobius strip to be the tautological line model one, but I think I'll just have to write it down, considering the time that already have lost. So all these straight, aka the tautological. So yeah, everyone knows about this tautological line bundle over. So I'm just gonna write it down. this is just like, so this is like R that is equipped with the right action of R of the units, right? So this is like, let's say, okay, so it is like basically it's like the blow up of origin. Yeah, let's write it. Fine. So sorry. Now let's. All right, now we are in a position to move to the game theory construction. So okay. So how do you think about it? So first, start off by noticing that this category that it has all the isomorphism plus vector bounds over X, right? So this has a monoid structure, monoidal structure. Five, okay, structure. No, so it has a monoidal structure that is induced by the Whitney sum, right? So, uh, so you maybe write it like this. So this is my Whitney sum. So this is a monoid. Okay, so now the idea is to apply group completion monoid, right? So group completion, like as you know, so we group complete and by formally adding inverses to get Z, right? Similarly for arbitrary monoid, you have the golden group structure, right? So, so uh, maybe yeah, I can recall there if you want, but okay, let me skip it. Or I can like recall that if you want the so for X, a topological space, right? So define K of X to be to both be equal. Right. So yeah, that was basically okay. And now we'll see. Right. So as I said, like the way you get a program group from a monoid, I basically translate it to this situation. So what do we have? So for okay. So you have these different classes. See that we call a class, like one of these classes, to be a virtual vector function. So this is equivalent class. If and only if there exists classes and fine. I'm just translating like total different instruction. So that right. Yeah, right. So, right, so one of these would be virtual, call them virtual. So let's do an example, like first thing that you do, so it's the K-theory of the point. So, right, so if you have a point, so this is just a category of X spaces, right? And isomorphisms of vector bounds, so think about it like this. So yeah, and the isomorphisms, as I was about to say, the isomorphisms are isomorphisms of vector bounds are bijective linear maps, like this case, right? So the thing is that like so as an isomorphism of finite dimensional vector spaces, so an isomorphism happens when like you have an equality of dimensions, like it has to do with dimensions, right? So using the fact that we can prove this. So now, so we know that if we could complete and look at set. So, right. So that was the first thing we'll do a few more examples actually. This is just like the first thing. And right. So now we'll kind of talk about the fundamental product theorem and Barth periodicity. Oh, wait. Now I recall it only in the title I have some. Oh yeah, it's just like the fun. So the fundamental product theorem and Barth periodicity, right? And then we'll see a few more examples, right? Okay, so let me see. Okay, so why do we? So what's the point of the fundamental product theorem? Like how to explain why we think about it? So it actually just helps us to determine the K groups of like n spheres and like product spaces. Like so that's like gives you a canonical way to calculate the K. So before we start, so let's see something in the setting of ordinary cohomology, like and try to relate that to so fundamental product. Just call it the fundamental product. So recall for ordinary cohomology, this is S2. I'll try to be you have something like this, just generated by E H. So this H is like the first Chern class of the complex line bundle on this two. So this H that you have. So we can show, right. So I can show now. So this is just the setting of ordinary cohomology now. So I assume it's like known and understood. So I'm trying to use it to see if I can get to the fundamental product here, right? So now so you can show that as a ring, like so as a ring you'll have this equals 0. So show 0. So that means that we can write something like this. Also remember, so reduced, if we take reduced cohomology. So okay, by the way, yeah, I also have to define reduced K-groups that I've not done yet. You have generated by H, right? There's something like this. So what the fundamental theorem states, so the fundamental product theorem states that the complex topological K theory of two sphere S2 behaves like ordinary cohomology if you just replace H by the bot element. So H replace H by the bot element. So that's the premises. So right. Okay, let's recall what or maybe just definitions of what reduced K groups are. So let me put it let me put it like let me define it like using functoriality. Okay. All right. So X is a pointed topological space, right? So you have a map, like you have a group homomorphism. All right. So by restriction um by restriction of a virtual vector model to a base point. It's basically the kernel of this model. Kernel of F basically gives us X. Sorry about the handwriting again. I totally see how much it sucks. Right. So we can actually prove that the bot element also squares to zero. So now note that so the bottom is the image of H and it's 2. So that comes from the fact that we have like that splitting like this. Right, yeah, you have a splitting of this form, so it's the image of H in reduced K of S2. Right? So you have a ring homomorphism that looks like this. So like more generally, if X is a topological space, okay, X, X. We have a composition. This is basically the external product forever. Okay. Right. So more generally for a so basically the fundamental theorem that is a proposition. Fundamental theorem just says that the yeah for X compact Hausdorff ring homomorphism which you saw ring homomorphism is so as a corollary to the fundamental theorem we'll get forward S is 2. So this is just a corollary. So it is an isomorphism. Right? So whoops. Sorry. I have to stop to take a glass of water. Excuse me for a second. Okay, ready to go. So yeah, do you have any questions or anything so far? And yeah, feel free to like, ask, like if you don't understand the writing because like it's really bad. You can see it. And also like it's a bit of a trouble as I'm just getting used to my tablet again. So I'm having to take turns looking down at the tablet. So it's a bit annoying, but you can manage. Okay, so let's see another example. More examples. More examples. So we'll use the fundamental theorem, like so using the fundamental theorem, we'll get like a complex of S2. And so okay, let's look at the torus. So for the torus, so this is like an argument. Oh yeah, I remember that okay of the torus is like the k of s squared, but okay. Let me try to remember that. Okay, I think. Yeah. So going to reduced k, you'll get something like this. This is the argument basically. There you go. That's one. So and yeah, okay. Yeah, that's right. So this will give us the S2. And these are zeros. Oh, sorry, that's one. So these two are zeros. And this will give us S2. So this is like short argument. Okay, so I see that I have 20 20-ish minutes remaining, so probably try to give it fast. So let's see. So now let's see what bot periodicity is. So okay, so let me stay. So I'll maybe give a kind of sketch of a proof, maybe we'll see. So X is a pointed X is a pointed this is a pointed compact Hausdorff space. So we have an ice. So this is like suspension. Right. So how do we so sketch of the proof? I mean, it's more or less like it is a proof. I mean, it's not a sketch, it's just a proof, but let's see. So we have this. So I'm using a few things here that I'm not explicitly stating, which makes it a sketch. Right. Oh, oops. This will give us the k of s x, and that is when you take the external direct product of x, and that will give us basically right. So yeah. So yeah, I don't think I have a lot more to say. Maybe or maybe let's all right, let's so just a remark. I'm not gonna add more to it. So for people who know, so topological K-theory again, I'll just probably say it. So topological K-theory is like it is a generalized Heisenberg Steenrod cohomology theory. So therefore, because it's a generalized cohomology theory, it is represented by spectrum. So you have this K-theory spectrum that you have. So that is basically that represents the K that represents the generalized cohomology theory that topological K-theory gives rise to. So that was it for the K-theory, for the topological K-theory part. Now, as promised, because I still have like 15 minutes, right? I'll talk about Waldhausen K-theory. So, all right, I'll just write it. Topological K-theory is generalized homogeneous theory. So is by the spectrum. So this is the spectrum. Right? So again, so for the part, so yeah, so that is mostly it what I had initially thought about talking in the talk. So this is something that I added, like excited to that I'll talk about all those very towards the end. So I'm not trying to fill any prerequisites. Like, if you know it, like if you don't, then it's totally okay. Right? So depending on whether you know it or not, but maybe get something out of the black box. It's Waldhausen K-theory. So here, so I'll start with the stable infinity category. So I'm not defined infinity categories at all. There's not what I was intending to, but like just to give a structure of the Waldhausen K-theory. So it is a stable infinity category. And so if we decategorify, like, so what do you mean by decategorification? So when you decategorify, you just have the objects modular equivalence. Equivalence in the sense of infinity category. So the decategorification is actually has a structure of an mutative monad. So you decategorify. You have a abelian monad that basically comes from the byproduct that you have. Right? This is the way you define it. So we can then pass on to the Grothendieck group to get an abelian group actually. So in fact, this is like the way think about Waldhausen K-theory, that you have like a split. We have split federation sequence. So something like this, whatever. Right, something like this, and right. So the thing is that again. So this is like another way to think about it more generally. So for getting such a result for an arbitrary cofactor sequence, right? We have to impose, okay, so these arbitrary, say for people who know these arbitrary cofactor sequences, I mean by that I mean distinguished triangles. So for arbitrary so I don't know, something like this. So you have to impose set. You have to impose that, and right. So this actually lets us to lets us pass to K0. K0 of C. So that is basically K. So more generally, so we have connective spectrum. Connective spectrum K. So that you get to the something like this. This is like the K0. And then you can, of course, define higher groups, K of C to N of K of C, right? So this is like actually Waldhausen K-theory, and So now, like for an abelian category, for now let's see how can we get our like instruction for topological K-theory using this definition. Yeah, so for abelian category, um, I so you define you actually write Ka to be K of so the K of the bounded chain complex. So this is the way I define it, right? So now we get the zero high topological K theory by defining A to be the category of vector models. And so that'll give us degree zero topological. Right. So this was about the construction. This was about the Waldhausen K-theory construction. I don't know, like how it sounded like really rough kind of a run through the construction without like black boxing a lot of things, right? And so let me maybe say a few things that I intended to talk about thematic things. Of course, I like that. I decided not to. So I just wanted to say that, like, that the formal group law again, this is for like maybe this is like for a very specific audience. Say that that the finite group law associated the complex orientation of complex topological gate theory. It basically gives us this non-multiplicative. So, and like for people who do thematic stuff, I mean, they already know that KU is basically the height one version in thematic filtration. So it's like KU is the infinity wing that the height of the complex KU. So, yeah, that's probably all that I wanted to say. So I will stop here. See if there are questions in the chat. Sorry. So maybe I can stop the recording and start the screen share.